We physicists have been waiting for a century, beginning in 1916, specifically, for this. The image shows a nearby black hole, which may be one of the most charming and baffling entities in the universe. These enormous beasts rule the cosmos with their immense gravitational pull, yet they remain intangible for all intents and purposes. A black hole with a possible mass of 2 to 4 million times that of the Sun has long been a subject of scientific investigation. Despite this, our understanding of them over the last 20 or 30 years has remained incomplete. However, we have been progressively gaining more knowledge. Recently, things have become even more intriguing. M. Kaku recently disclosed that we have finally been able to examine the contents of a black hole. This new information clarifies nuances that the scientific community may have overlooked from the beginning. As we continue to investigate black holes and reveal the secrets of space, we must first discuss the fundamentals before diving into what Kaku discovered. Our comprehension of black holes is still incomplete. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. However, the concept of black holes remained purely theoretical for another 50 years. It took seasoned scientists decades to find evidence proving their existence. This breakthrough occurred in the 1960s when researchers were observing the star X-1. They noticed a stunning luminous blue star emitting X-rays, despite being in orbit around a massive, seemingly lifeless object. Further examination revealed that these X-rays were not moving independently but were instead being drawn into the dark object. This led to the term black hole. This discovery filled a major gap in our understanding. It proved that black holes are not merely an abstract concept or a byproduct of Einstein's imagination, but real celestial entities. While this was a remarkable revelation, it also highlighted the urgent need for more information. Scientists worldwide began studying this black hole, which was eventually named Cygnus X-1. It is located in the Cygnus constellation, approximately 6,000 light-years from Earth. This discovery was no small feat. Cygnus X-1 shines far brighter than the Sun and, due to its extreme density, has an incredibly strong gravitational pull. The force is so immense that even light cannot escape, which is why it is referred to as a black hole. Black holes are both fascinating and terrifying. They are regions of space where gravity is so overwhelming that nothing, not even light, can escape once it crosses a certain threshold. If anything comes too close, it is pulled in forever. This danger only increases their significance in scientific research. The discovery of Cygnus X-1 was just the beginning. Scientists began searching for more black holes and estimated that there may be nearly 100 million of them in the Milky Way alone. However, because they are extremely difficult to detect, we still do not have an exact count. Current estimates suggest there are a few million black holes in our galaxy, making them crucial objects of study. One of the key aspects of black holes is their immense gravitational force. Anything that enters a black hole is crushed to an extreme degree, becoming part of the singularity, a unique feature at the core of a black hole. To put it simply, black holes are like cosmic vacuum cleaners, consuming everything in their path. If a person were to fall into a black hole, they would undergo a process called spaghettification, gradually stretching into a single line before ultimately being destroyed. This extreme gravitational effect is why no one should ever approach a black hole. Fortunately, the closest known black hole is nearly 500 light-years away from Earth, though even that is close enough to raise questions about potential risks. In 2021, scientists achieved another milestone, capturing the first clear image of a black hole. This image was of the M87 black hole and was taken over multiple nights. Researchers compiled individual photographs to fill in gaps, confirming that black holes are not just empty voids but highly complex structures. Black holes have 3 distinct layers. 1. The event horizon. This is the outermost boundary, the point of no return. Once anything crosses this boundary, it is inevitably pulled into the black hole. 2. The photon sphere. This is the region where light orbits the black hole. Any light that enters this area is trapped and cannot escape due to the immense gravitational force. 3. The singularity. This is the innermost region where everything that falls into the black hole is crushed into an infinitely dense point. At this stage, the known laws of physics break down, making predictions impossible. Each black hole is unique, though they generally follow this 3-layer structure. However, their individual properties can vary significantly, which makes them even more intriguing to study. Scientists cannot directly observe black holes because anything that crosses the event horizon is lost forever. Instead, they study them indirectly by analyzing the radiation, gases, and dust surrounding them. Inserting a probe into a black hole is impossible. It would be pulled into the singularity and destroyed before any useful data could be transmitted. This fundamental limitation forces scientists to study black holes using alternative methods. Adding to the complexity, the interior of black holes defies conventional physics, making their study even more challenging. Despite this, researchers continue to develop new theories and models to better understand these mysterious cosmic phenomena. Because black holes break down the known laws of physics, they remain one of the greatest mysteries in modern astrophysics. Scientists have spent decades formulating theories to explain their nature, but many questions remain unanswered. One of the biggest mysteries is what happens to matter and information that falls into a black hole. According to general relativity, anything that crosses the event horizon is lost forever. However, quantum mechanics suggests that information can never be truly destroyed. This contradiction has led to the famous black hole information paradox, a problem that remains unresolved to this day. The Hawking radiation theory. In 1974, physicist Stephen Hawking proposed a groundbreaking theory that black holes are not entirely black. According to Hawking radiation, black holes emit small amounts of radiation due to quantum effects near the event horizon. Over time, this radiation causes the black hole to slowly lose mass and eventually evaporate. If Hawking's theory is correct, it suggests that black holes are not eternal, they eventually disappear. But this raises another problem. If the black hole evaporates, what happens to the information that fell into it? Is it truly lost, or does it escape in some form through Hawking radiation? Scientists are still searching for answers. Wormholes and the possibility of time travel. Another fascinating theory related to black holes is the idea that they might serve as wormholes, shortcuts through spacetime. Some physicists speculate that if a black hole connects to a white hole, a theoretical object that expels matter instead of absorbing it, it could create a tunnel between distant points in the universe. This concept is popular in science fiction and has led to discussions about time travel. If an object or person could survive the intense gravitational forces inside a black hole and pass through a wormhole, they might emerge in a different part of the universe, or even in a different time. However, no evidence of wormholes has been found, and most scientists believe that the extreme conditions inside black holes would make them impossible to traverse. Supermassive black holes and their role in the universe. While small and medium-sized black holes are scattered throughout galaxies, the most powerful ones are known as supermassive black holes. These giants, with masses millions or even billions of times greater than the Sun, sit at the centers of most galaxies, including our own Milky Way. The Milky Way's supermassive black hole, known as Sagittarius A*, is located about 27,000 light-years from Earth. Scientists believe that these enormous black holes play a crucial role in galaxy formation and evolution. Their gravitational pull affects the movement of stars and gas clouds, shaping the structure of entire galaxies. In 2019, the Event Horizon Telescope, EHT, provided the first-ever image of a black hole, the one at the center of the galaxy Messier 87, M87. This historic achievement confirmed many aspects of Einstein's theory and provided a visual representation of a black hole's event horizon. The future of black hole research. As technology advances, astronomers are developing new ways to study black holes. Some future missions and research areas include next-generation telescopes. Upcoming space telescopes, such as the James Webb Space Telescope, JWST, and future radio observatories, will provide more detailed images of black holes and their surrounding environments. Gravitational wave observations. The discovery of gravitational waves, ripples in spacetime caused by black hole collisions, has opened a new way to study them. Observatories like LIGO and Virgo continue to detect these waves, offering insight into how black holes merge and grow. Simulating black holes. Scientists use supercomputers to simulate black hole behavior, helping us understand how they interact with their surroundings. These simulations could provide clues about what happens inside the event horizon. Searching for primordial black holes. Some researchers believe that tiny black holes may have formed in the early universe. If detected, they could provide valuable insights into the origins of the cosmos. Conclusion. Black holes remain one of the most enigmatic phenomena in the universe. They challenge our understanding of physics, raise profound questions about the nature of spacetime, and continue to be a source of fascination for scientists and the public alike. While much has been discovered in the past century, many mysteries remain. As new technologies and theories emerge, we may one day unlock the full secrets of black holes, perhaps even discovering what lies beyond the event horizon. Black holes, and things get worse with each one. One of the most fascinating and compelling explanations for their formation is the fact that they are constructed from stars that have collapsed. By the time a star runs out of fuel and can no longer generate sufficient energy to combat the force of gravity, which never stops pulling inward, the star begins to collapse into itself, shrinking and becoming more dense. If the star is large enough, this process can continue until it changes into a singularity. To determine the nature of black holes, NASA researchers focused on the center of the universe. Astronomers observed M87, an extremely hot whirlpool with a massive amount of hydrogen gas spinning at an astonishing speed of 1.2 million miles per hour. The sheer force of the gas disk's rotation should have caused it to disperse in all directions, but it did not. Researchers discovered that something massive must have been at the center of the galaxy, preventing this from happening. This enormous object weighed between 2 and 3 billion suns and was likely a black hole. However, that does not appear to be the only theory. In 1963, Roy Kerr, a New Zealand mathematician, used Einstein's gravity equations to give the most accurate description of a rotating black hole. He demonstrated that a rotating black hole could not collapse into a single point, as previously expected. Instead, it would form a fire ring, or a thin disk that rotates so quickly that external forces prevent it from collapsing. This disk of matter is called the ergosphere. The area around the black hole is where physical laws begin to break down. However, the most fascinating aspect of Kerr's model was that it predicted the presence of an Einstein-Rosen bridge, also known as a wormhole. A wormhole is a hypothetical passage through time and space that connects two distinct regions of the universe or even two parallel universes. The idea is that instead of being crushed into oblivion, an object could pass through a tunnel, traveling through the fire ring and emerging into a parallel universe through a white hole. To comprehend how this works, we must examine Einstein's theory of spacetime. Our reality is not made up of distinct elements but is linked together into a four-dimensional fabric known as spacetime. Massive objects warp this fabric, creating gravitational fields that cause other objects to move toward them. Now, imagine a piece of paper representing spacetime. If you place 2 points on the paper and draw a line between them, this represents conventional travel through space and time. But if you fold the paper in half so that the 2 points touch, you create a shortcut. That is the fundamental concept behind a wormhole. Wormholes are more than just science fiction. They are a prediction of general relativity. However, no one has ever directly observed one. This is because wormholes are inherently unstable and likely to collapse quickly. But the existence of an Einstein-Rosen bridge suggests that black holes may be more than just enormous vacuum cleaners. They could serve as gateways to other regions of spacetime. Could we traverse the universe through a wormhole? Sadly, the answer is most likely no, at least not right now. Even if we could stabilize a wormhole, it is unlikely that we could use it to travel faster than light. Einstein's special theory of relativity suggests that the speed of light is an absolute limit on how fast anything can move through spacetime. Despite this, the theory that black holes and wormholes could act as access points to different parts of the universe, or even different times, has been a fascinating topic of speculation among physicists for decades. If there were ways to circumvent the structure of spacetime, enabling travel across vast distances or even backward in time, it would be revolutionary. One of the most intriguing concepts in this field is the CR wormhole. After Roy Kerr described how Einstein's gravity equations apply to wormholes, physicists proposed that a theoretical tunnel through spacetime could link two distant locations, potentially even two different universes or time periods. The CR wormhole is theorized to exist in our universe, shaped like a ring, much like the mirror in Alice in Wonderland. In theory, it could transport a traveler to another universe or another time, where the physical laws might be entirely different from those we are accustomed to. While the idea of wormholes as portals for galactic travel or time travel is exciting, physicists debate whether they would be stable or even traversable. High levels of radiation and subatomic forces surrounding black holes could make crossing them impossible. Einstein's gravity equations describe wormholes and black holes but do not account for quantum forces that govern subatomic particles and radiation. To fully understand these phenomena, physicists need a new explanation that unifies quantum mechanics with gravity, often referred to as the theory of everything. This theory would combine Einstein's gravitational model with quantum mechanics, which describes how subatomic particles behave. One promising candidate is superstring theory, which proposes that all fundamental particles are actually tiny vibrating strings. In this framework, different vibrations of these strings correspond to different particles, much like different notes on a violin produce different sounds. Superstring theory suggests that these strings shape spacetime itself, forming black holes, wormholes, and other exotic phenomena predicted by Einstein's equations. However, there is a catch. Superstring theory requires extra dimensions of spacetime, so tiny that they are undetectable with current technology. While the theory offers a compelling way to unify gravity and quantum mechanics, its predictions remain untested.